Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. The webinar today will consist of a brief overview of both programs, followed by technical discussions on improving the treatment of oil and water emulsions in shipboard Bilgewater to help DoD increase the volume of wastewater which can be discharged to open waters. We'll start off with Dr. Carrie Dutcher from the University of Minnesota, who will discuss emulsion studies using macro and micro scales to quantify key properties defining emulsion stability and destabilization. Carrie's presentation will be followed by a Q&A session. Then, Ms. Danielle Painter of the Naval Service Warfare Center will present her work on developing a model emulsion based on commercial off-the-scale detergent used by the Navy and experimentally evaluating emulsion stability under different conditions. Danielle's presentation will also be followed by a Q&A session, and we will conclude the webinar with a longer Q&A session featuring both of today's speakers. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, try creating a free Zoom account, and this should allow you to view the webinar slides using a compatible internet browser such as Firefox, IE, or Edge. If your screen freezes, try keying in Control and F5 to perform a hard refresh of your screen. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, please call into the conference line shown here. You may also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for the speakers. In case of continued technical difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. So that's another option for you to follow the presentation. One last thing before I turn this over to Robin, today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A sessions to submit your questions. We do encourage you to submit questions as you come up with them. And when you submit your questions, please make sure to add your organization name so that we can identify you during the Q&A sessions. And with that, I would like to introduce Dr. Robin Nisan, who is the SERDP and ESTCP Program Manager for Weapons, Systems, and Platforms. And before joining SERDP and ESTCP, Robin worked at Navarre's Weapons Division, China Lake in California. Robin, please proceed.
Thank you, Rula. Let's click a few more times. Pleased to welcome everyone to today's SERDP and ESTCP webinar. So SERDP is the Strategic Environmental Research and Development Program. It was established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development, which will ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program. In this program, we demonstrate innovative environmental and energy technologies. These investments capitalize on past work done under SERDP or other research programs, and they're designed to transition technologies out of the laboratory and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. There are 5 program areas in SERDP and ESTCP. Installation, energy, and water is ESTCP only, whereas the other 4, installation, energy, and water, munitions response, resource conservation and resiliency, and weapon systems and platforms, are both SERDP and ESTCP programs with one program manager. Today's webinar focuses on weapon systems and platforms. The Weapon Systems and Platforms program area has these major focus areas: surface and engineering sciences, energetic materials and munitions, noise and emissions, waste reductions, as well as lead-free electronics. For future webinars in our series, you'll see that we cover all of the program areas, and we have one coming up on dioxin treatment. In July, we'll be doing one on securing DoD control systems and infrastructure from cyber threats. At the end of July, predicting PFAS fate and transport. And then we go into threatened and endangered species, approaches for managing contaminated sediments, and munitions response. Here's where you can find information on upcoming webinars. Finally, I want to talk just a little bit about the upcoming SERDP and ESTCP symposium. This symposium will be held the first week of December, and we're moving forward pretty quickly. So an agenda is already out there, a tentative draft agenda is out there. And we're also monitoring the COVID-19 situation, the pandemic, and we'll be determining if we're going to be able to have this symposium as a real live symposium or if we need to go virtual. But in the meantime, our plans are to proceed with a real symposium. So with that, I want to say I invite you to enjoy the webinar today and thank you for participating. Back to you, Rua.
Thank you so much, Robin. It is now my absolute pleasure to introduce our first speaker, Dr. Carrie Dutcher, who is an associate professor of mechanical engineering, chemical engineering, and materials science at the University of Minnesota, Twin Cities. Carrie's research interests include complex fluids and multi-phase flows, including emulsions, suspensions, aerosols, and foams. She has received a number of early career awards, including the NSF Career Award. And prior to her faculty position at the University of Minnesota, Carrie was an NSF Atmospheric and Geospace Sciences postdoc research fellow in the Air Quality Research Center at the University of California, Davis. She received her bachelor's degree in chemical engineering from the Illinois Institute of Technology and her doctoral degree also in chemical engineering from the University of California, Berkeley. Carrie, we're happy to have you. Please proceed.
Well, hello, thank you very much. I'm excited to talk to you about work that we're doing at the University of Minnesota on characterizing shipboard bilgewater emulsions using macro and microscale flows. So I'm going to begin by talking about the need, the background, and the key challenges of looking at these bilgewater systems. I'll highlight some of the approaches that we're using, including complementary techniques of macro and microscale flows, and some of the results that we're finding. I'll end with conclusions and takeaways for the DoD. So shipboard bilgewater emulsions are oily wastewaters that are formed in the bottom chamber or the bilge of the ships. Water that becomes on board ships will move down to the bilge of the ship and pick up contaminants like cleaning agents, lubricating oil, solid particulate, diesel fuels, and engine oils. and you can't simply discharge that water back overboard. Any waters containing more than 15 parts per million of oil must either be treated shipboard to remove that oil, or it must be stored and accumulated, and then you wait until you dock and then can treat it shoreside. So there's a need for improved mitigation strategies in order to meet regulatory compliance and increase the volume of water that can be discharged overboard. In order to enable these new strategies, we first need to improve our fundamental understanding of these systems. What are these emulsions made of? How are they formed? When are they most stable or most unstable? And in what conditions can we most readily destabilize them? So first I want to give you an overview of what the emulsions look like and how we treat them. You see an example here in this image of an emulsion that we made first by agitating the system to put oil droplets into water. But what you're looking at is not the emulsion right after it's formed, but rather after several days. And you'll see at the top, one thing that might jump out at you is that there's this brown looking liquid that's sitting on top of the rest of the liquid. That's the oil layer that forms when these larger than tens of micrometers in size droplets come out of solution. They readily cream out of solution. They form an oil layer that sits on the top. So you might imagine that's a great way to do an initial treatment of these systems, that you could use settling tanks or gravity-based plate separators and then skim the oil off the top or to draw the water from beneath it. However, that water underneath, if you zoom in, it's still filled with oil droplets. That these drops that are smaller in the order of tens of micrometers and smaller, they remain suspended in solution. They're susceptible to Brownian motion, and they remain suspended from the order of days or weeks or longer. And so these are drops that are too small to settle without aid on reasonable timescales, and you have to use some kind of secondary treatment, something that uses something other than gravity to remove these droplets. So you may imagine using something like a membrane where there's a chemical attraction of the droplet to the surface and phys absorption that can happen.
So the first challenge, like I was saying, is they're highly chemically stabilized. So these waters will pick up detergents like deck cleaners, they'll pick up soaps from personal care products, and these cleaners and soaps contain surface active additives called surfactants that make them such great cleaners. But these surfactants have molecular properties such that part of their molecular backbone is attracted to water and part of it is attracted to the oil phase. So anytime there's an oil interface, the surfactant molecules that are diffusing in the water phase will, if they're close to the interface, will absorb onto that interface. And this acts to lower what's called the interfacial tension, or lower the excess energy per unit area. And when you do that, you lower a thermodynamic driving force for the system to phase separate. That ordinarily oil and water does not want to be mixed together. They want to phase separate. But the presence of surfactant lowering this excess energy makes it more stable in the solution and much more difficult to separate. A second challenge is that this process of surfactant stabilizing interfaces is dependent on the size of the dispersed phase droplet and how curved that interface is. If I take the same exact chemical system and I measure that interfacial tension value, the results I get will depend on the size of the droplet I examine. So this data here is showing you results for water droplets that have been entrained in diesel fuels. And we're measuring interfacial tension as a function of time. And you'll see that it changes as a function of time. And that's because these diesel fuels contain additives that improve performance and reduce corrosion. But these additives will also stabilize the entrained water droplets, which you would want to remove from the fuel. And so if you take if you take a drop that's on the order of around 2 millimeters in size, which from the surfactant perspective is relatively flat interface, the surfactant will go to the interface, drop the interfacial tension value from around 20 millinewtons per meter to around 5 in the course of about 10 minutes. That same system, if you perform experiments on around a 90 micrometer size droplet, it will also drop the interfacial tension value that same range, but on the order of just a few seconds. And to put this in context for you, if the emulsion has this IFT of around 20, that's quite easy to break that emulsion and to treat it.
and an IST of around 5 is quite difficult. So if you had a high emulsification step like a pump, and then you had a filter downstream of that with a residence time of a few seconds, if you're using the Pendant drop data, you may think this would be quite an easy emulsion to break, but in fact, it's difficult. And what's happening is that the reason why there's a difference is that the surfactant transport mechanism changes from a diffusion limited on the bulk scale to a kinetic or absorption limited process. So we're looking to understand these stabilization processes as a function of composition, surfactant type, and oil composition, how these emulsions are stabilized and how they can be destabilized. And we have complementary approaches of microscale and macroscale flows. On the microscale, we use droplet microfluidics. This allows us to make individual droplets that we can then manipulate. There's high throughput of these droplets. It creates drops hundreds or thousands in the course of seconds or in the course of the time we examine it. And they're monodispersed, so they're the same size. So if we're trying to study size effects, this is a great way to do it. We have drops on relevant sizes in that difficult to separate regime, and then we can manipulate the droplets to measure them. But then we always want to see this, what we're measuring the individual level, and then compare it to what we're seeing on the macro scale. So we make whole emulsions and see the time scale for the emulsions to destabilize, both in static environments and then environments that where there's flow present. So shearing flow, and then we also use what's called Taylor-Couette flows. This is flow between concentric cylinders, where as you increase the angular velocity of the cylinders, and particularly the inner cylinder, you can cause the flow to go through a series of transitions from laminar unidirectional flow states through flow states where there's toroidal vortices and waves, all the way up to flow states where there's turbulence. And these cascaded transitions happen at well-defined critical conditions, and each one of the flow states have particular turbulent intensities and flow types. You can see how each one of these different types of flows impacts the emulsion stability. So as I mentioned, one of our techniques is microscale flows, and showing you some examples here. So we study drops on a chip, but we even make the drops on the chip. And if you look in the bottom left corner, this is an example of one of those drops being formed. This is a T-junction geometry, where one of the phases coming in through one of the bottom channel, and then the channel moving from left to right is the continuous phase. And you're seeing the drop right when it's about to be formed, where in these low flow regimes, you have the viscous drag forces overwhelming the capillary or surface tension forces, and it forms the droplet. So we don't want to just form droplets and leave it like that. We then want to manipulate them in some way and look at their response. So we send them through geometries where the flow field changes, or we trap them and perturb them. And that response to the drop, the shape oscillations and deformations, can tell us information about those interfacial properties, things like interfacial tension. So one of the systems we studied is the simulated Bilgewater system, and I just want to talk about what that is. So this is the new simulated Bilgewater mix number 4. And in the oil phase, you'll see things like diesel fuels and lubricating oils. And then the detergent phase, this is what you add to the aqueous or water-rich phase. That contains things like Tide and degreasing solvents. So when we perform experiments on the microscale, what we see is just like we saw with water inside a diesel fuel, these systems are also highly size dependent. That drop of interfacial tension happens about 10 times faster for micrometer droplets than its counterpart on the macro scale. And we also see that even simple oil-water systems are still complex. Even if we don't add any extra detergent in the water-rich phase, we still have a time-dependent interfacial tension response. And that's because even the diesel fuels and lubricating oils have additives and surfactants in them. So even if it's not picking up these cleaners, it's still having stabilizing agents that will stabilize the oil in the water. The other thing we see, and this is quite interesting, is that the phase matters for these small droplets. So I've described all of this in the context of a wet bilge where you have oil and water. You can also have water droplets in the oil oil-rich phase. And if you perform experiments on a Pendant drop on the millimeter scale, if you take the same chemical composition and you look at the interfacial tension as a function of time, you're not going to see a lot of difference in the interfacial tension profile. Maybe it'll be a little faster depending on the surfactants in the continuous or dispersed phase, but it's going to reach the same equilibrium interfacial tension value. But as you drop down to the micrometer scale, when there's a high degree of curvature, the surfactant approaching from the concave versus the convex side will impact the final equilibrium coverage, or at least the sterically hindered coverage available for that interface, and it'll impact the final equilibrium value. So we perform measurements with the detergent mix, but then also wanted to compare that to both model surfactants, well-known surfactants, sulfonated and hydrocarbon-based ones, AES, Triton X, SDS, as well as cleaners that are brought shipboard. So I just labeled them here, cleaners A, B, and C, and you'll hear more about these later in the next talk. But just to point out here that these surfactants vary in molecular weight, so in size as well as molecular structure, and they can even vary in how if they're charged or not. So they're quite different from each other. And we can use the macro scale measurements, the pendant drop measurements, to determine critical micelle concentration. So we perform experiments at different concentrations, and then we find at what concentration do you no longer change the equilibrium interfacial tension value. And so that's how much you can pack at that interface, and after that, the surfactants will form these spheres or micelles in the bulk phase. You can take the gradient of the interfacial tension with respect to log of concentration, and you can find the maximum surface coverage of the surfactant at the interface. You can also, depending on the isotherm that you're using for your analysis, you can find different types of equilibrium constants. So if you use a Langmuir isotherm, this is called the Langmuir constant, and it's a sort of affinity for the surface. So it's how much the surfactant likes that interface. And I've shown you a line chart here of the equilibrium constant for the 7 we measured, and then we just compared it to a few others. And you'll see that the 3 cleaners that we've been studying actually compare quite closely to something like Triton X. And then you can also determine diffusivity as well. From the microscale measurement, because you're pushing to a regime where it's no longer diffusion limited, but rather absorption limited, you can also measure things like absorption rate and desorption rates of the surfactant, the rate at which it can get onto and then off of that interface. And we think that these are quite important as well for stability. If you think about what actually has to happen for droplets to destabilize, something like coalescence, if true drops come together, there's this thin surfactant-laden film between the 2 droplets. And that film has to thin and dimple and then rupture and break in order for the drops to come in together and coalesce in the treatment process. In that process of dimpling and rupture, there's in the dimpling process, there's a local change of the curvature that's happening, and soluble surfactants will get pushed off that interface, and they have to reabsorb back on. So if the rate at which it reabsorbs is faster than the rate at which the dimpling, the thinnings happen, you may be stabilizing that interface versus destabilizing it. So we also compare the absorption rate of our systems and our cleaners to these other known surfactants as well. And our question here is, which, if any of these wide variety of parameters that we're measuring seem to be correlated, or at least maybe even deterministic, of the stability of the bulk emulsion. So that just leads me to the second section, where we're looking at the emulsion as a whole and the timescales at which you can destabilize these systems. So I'm showing you here those vials again that you saw on an earlier slide. And for these systems, as you move from left to right, you'll see the 10% down to 0.1%. That's how much oil is present by volume. And so you'll see the ones with the most oil appear sort of white, and they're cloudy. They're highly turbid environments because they contain so much water that's reflecting the light. And then over time, that's going from top to bottom, you'll see that that oil layer has formed on top, and you have a more transparent water layer beneath. And so when you're thinking about timescales for destabilization, there's several things you could do. One thing is to look at the rate at which that oil layer forms, the oil separation. You can also look at, and this is what we look at, the rate at which the turbidity changes. That's how cloudy it is. But these are good methods that gain some information about stability. They're not perfect methods. And it's helpful to complement these methods with looking at the size distribution of the droplets themselves. So as as time passes, the droplets, maybe they're just creaming out of solution, but maybe they're also ripening or coalescing, or there's some other mechanism that's going on. And so to get size distribution, you can simply just look at your emulsions under an optical microscope and use some image detection at the radius of these droplets. You have to use a process of laser diffraction, so another optical technique that's looking at how much light is diffracted. And for our homogenization methods, we're seeing systems where the drops are in the order of 1 to 10 micrometers in size. It will depend on how you prepare it, though, so how much power you've put into the emulsion when making it. So we use a Turax homogenizer. This is run it at tens of thousands rotations per second, about 20,000 rotations per minute. I mean, you know, into a certain amount of volume for a certain amount of time. And this is how we get our distributions. We then look at how the turbidity and the size distribution evolve with age. So on the left, you see again the cloudy, highly turbid environment. This has a lot of droplets. They're scattering a lot of light. And then over time, it's come out of solution. And for this particular sample, and this will depend on how you sample it as well, you see a shift in the size distribution. They appear to shift to larger sizes. And it would indicate that some of the smaller droplets are perhaps coalescing or ripening into the larger ones. So if you were to track the turbidity as a function of time and then plot it out, you would see that it forms a nice single exponential decay. And if you fit this to an exponential decay, you'll get a time constant that's related to the stability. So that's plotted here. It's this time constant versus percent of oil. And a time constant of 0 just means it's instantly unstable, that the system would just instantaneously separate into oil and water. A time constant of around 100 here means that it has a characteristic time scale of about 100 hours for the system to phase separate. So I'm just showing a representative example of how these time constants change with composition. You're looking at the naval simulated bilge mix number 4 and distilled water DIST, as well as the model oil mineral oil. And then we took those same systems and we looked at a synthetic seawater, so something with higher salinity. And in both cases, both model oil and the simulated oil, we see a drop in stability in the presence of salt. And we expected this. The salt will change the behavior of the surfactant. Each one of these points are made with the same amount of added surfactant. And then they all start with the same initial size distribution. So salt will definitely destabilize these systems for this particular case. But another thing that we thought was a bit more interesting was that there was any dependence on oil percent at all. So if you look at the distilled water cases, you'll see first an increase and then a decrease. And I don't know if I would have expected that going in, but if it was just about the creaming rate, a 10 micrometer droplet would cream at a certain rate and come out of solution at a certain characteristic time scale, and it wouldn't matter if there's another one of that same size scale present. And so the fact that there is a dependence tells us that there's some sort of droplet-droplet interactions that must be happening. And so in collaboration with other sort of supported emulsion groups at Purdue, John Howarder and Kendra Irk and colleagues, we're seeing that this initial increase seems to be due to hindered creaming effects. That these large droplets, yes, they would ordinarily, if unhindered, will come out at a certain rate. If they have to travel centimeters and they've got 10,000 slower moving droplets ahead of them, they have to get around them. And if there's some sort of colloidal scale and attractive interaction, then all the more then they'll be dragged down and slowed down. So there seems to be an increase of hindrance to a critical point. But then after that, it seems to destabilize again. And this is likely due, again, for the same surfactant concentration, the same initial size distribution. If you add more oil, you're also adding more interfacial area. And so then you begin to see a drop in the surface coverage. And so when you begin to have these collision events between oil droplets, you could also have destabilization, binary destabilization happen. So perhaps they'll coalesce into each other or ripen and they form a larger droplet, and then they rapidly come out of solution. So in addition to looking at static systems, we're also looking at how these systems evolve in shear. So you would expect that droplets on a faster streamline, and this is a well-known phenomenon, will collide into droplets that are along a slower streamline. So this is a way to promote droplet collisions and then to have some sort of destabilization happen. And so you can measure the effect of shear in something like a rotational rheometer, and that's what's shown here. And so you'll measure turbidity and size distribution. You can also measure viscosity because it'll be sensitive to changes of viscosity as the oil creams out of the solution. And what we're seeing is that there is clear destabilization that happens for systems with high oil percents in these simple shear environments. That over 10 weight percent of oil, we see actually quite a dramatic creaming out of these emulsions. But we don't see that same result for systems where there's less than 1 weight percent oil present in the system. That it follows the same viscosity as a function of shear rate profile. It has the same size distribution that you initially put into the system afterwards. So you can't destabilize these lower oil content systems with simple shear. We then test our simple systems in the Taylor-Couette geometry. So as I mentioned earlier, this is a geometry where we can vary the flow fields. And it's a nice way to develop flow fields where you can have small-scale local recirculation that's well controlled. So the first instability is Taylor vortex flow, which is counter-rotating toroidal vortices. But as you increase the angular velocity of the inner cylinder, it cascades through transitions where you begin to form other temporal frequencies. You begin to have small-scale chaotic recirculation happening within the vortex. And for these systems, we are seeing destabilization happen for our emulsions for the low oil content systems. So systems with less than around 1 weight percent of oil, we see a shift where you'll have a reduction in the number of small droplets and enhancement of the number of large droplets, especially when exposed to things like the turbulent wavy vortex flow states. Okay, so I just want to wrap up here and just to emphasize that it's important when looking at multi-phase systems to perform measurements at length scales that are applicable to your application, that the surfactant transport and even the time scale for emulsion stability is going to depend on the interfacial curvature and the droplet size of the dispersed phase, and that these destabilization rates are variable with surfactant type, with oil percent, with salt content, as well as the environment that they're exposed to, so the flow type and mixing conditions. So ultimately, we're trying to improve mitigation strategies to enable enhanced removal of the oil to below that 15 parts per million mark, and then enhance the way in which we separate. We've developed new measurement platforms on the macro and micro scale for looking at these particular systems. And you imagine ones like the microfluidic flows could even be diagnostic for how difficult an emulsion would be to break that you could test there locally. We've developed a database of dynamic parameters, both surfactant, a number of different surfactant properties for these cleaning agents and the model surfactants, as well as tested the emulsion stability for a number of different conditions. And then our goal here is to inform the operation and then the mitigation strategies, both with our individual study and then as a collective, all the teams working on these systems working together. I'd like to acknowledge Dr. Yoon Chen, a postdoc in my group, who worked on the microfluidic measurements, as well as Tom Neumiller, a recent graduate in my group, who performed experiments in the bulk stability analysis and the Taylor-Couette flows. And then I'd be really happy to take any questions. Thank you.
Great, thank you so much, Carrie. As a reminder, you may submit questions by using the Q&A box on your screen. We have received a number of questions on this first presentation that Carrie will answer. Starting with this, Carrie, how do you select surfactants and other ingredients? What's the process?
Yeah, so that's part of working with the team of people. So I would say, especially the folks at the Naval Surface Warfare Center, the Carteret Division, they've been really informing what's the best mimics for what's seen in the bilge. And you'll hear from Danielle next about this. So that's how we got the initial naval simulated bilge mix that we used. And then in terms of the model surfactants, we went with both the surfactants that are commonly found in these detergents, so the most common ones found in things like Tide, as well as ones that are really well characterized, things like Triton X. And then the cleaning agents, that's simple. It's what cleaning agents are allowed to be brought aboard the ship. So those are for the surfactants. In terms of the oil phase, you know, there is a great deal of variation in the engine oils and the diesel fuels. It's helpful if you can find model systems that capture properties of those. So we use things like mineral oil, but then in terms of the diesel fuels, there's a number of different model systems you can use that it's hard to exactly match diesel, but you can match either the viscosity or interfacial tension pretty well, or you can match things like solubility as well. So you just sort of think about that. What is the best mimic systems for things found aboard the ship?
Great, thank you, Carrie. Another question for you. What are the limits to your measurements? For example, what governs the lowest droplet sizes detectable in your turbidity measurements?
Yep, yeah. So yeah, turbidity in general is not a perfect measure. So how much light gets scattered, because a lot of things will influence the way light interacts with particles. So certainly the number of particles will influence, and that's what we're trying to get at, the concentration. But the size of the particle will also impact that. And as you move down to droplet sizes that are in the order of the wavelength of the light, it begins to interact with light quite differently. So you really want to be above that when you're thinking about these turbidity measurements and trying to get meaningful information out of that. So that's for all these optical techniques, that's what you're sort of thinking about. Are you above that wavelength or not?
Great, thank you, Carrie. This is a question from Texas A&M University. What is the impact of microparticles in the water phase? Do you have any concerns about particles stabilizing the interface or surfactants destabilizing it?
Yeah. So if you're thinking about solid microparticles, absolutely. These particulates will act to stabilize the interface, and it's certainly something that should be included in a number of studies. I do believe Carter Rock may be presenting on that. I know they've looked at that a bit, but solid particulate will stabilize interfaces, as well as you might have some absorption of the surfactant onto those particle surfaces depending on the chemical structure of the surface. So they do play a role.
Great, thank you. What about systems with mixtures of surfactants instead of single surfactant? How would you perform the analysis, and would it impact the results that you've observed?
Yes, so right, a lot of our analysis, when you go from the interfacial tension data to getting information about the surfactant, you have to assume equation of state and an isotherm that correctly governs what's going on. And so if you have multiple surfactants, there are extended versions of these isotherms, but you want to be sensitive to how the surfactants might be interacting with each other, especially if you have, a neutral and a charge, or things with very different molecular weights or diffusivities. One might be getting to that interface first and the other one later. One might be more soluble in the outer phase, one might not be. So it's something that we think about, but we're trying to think about more moving forward. So in the follow-on project, we're looking not just at these single surfactants, but mixtures of surfactants. Because if you take the data just from a single surfactant A and surfactant B, and you put them together, you can get quite different results, non-additive results, with the combination of the two. So trying to understand that process.
Great, thank you, Carrie. This is a question from Lehigh University. Would you recommend a standard method, or is there a standard method for studying the droplet density in the bulk of the liquid?
So I don't know if I can follow up. Is that in regards to the actual homogenization of the system?
It has to do with the droplet density in the bulk of the liquid. So let's assume it is regarding to that, and let's take a crack at the answer, and then we can follow up afterwards.
Great. You're right, because if I say something like I'm putting 10 weight % of oil, what does that mean in terms of, you have to know what the droplet size distribution is to know anything about the concentration and sort of how far a drop has to go to run into another drop. And so it's important to look at different homogenization methods. So some groups will look at both high homogenization and low homogenization, and then study these same parameters. What are the timescales for separation and oil separation? Yeah, so I think it's important to do both, to look at the ways in which you homogenize the system.
Great, thank you. Do you see an effect of particles for an extracellular matter produced by bacteria on the stability of the emulsions?
I haven't looked at that, but that's a great point. So that's another way that you can get a sort of additives that would stabilize the system. But I haven't looked at that, no.
All right, thank you. And maybe one last question here before we move on to Danielle. And again, we'll revisit any additional questions that come in towards the end of the webinar in the interactive Q&A session. So this is a question from W2E. Is there data available on the quantity versus range of droplet size in Bilgewater oil water emulsions within the DoD sphere?
So within the bilge, like you said, I'll take a crack at the answer and we can do feedback. You have to monitor how much oil to see if you're below that 15 parts per million. And so they have, they run a monitor, a turbidity-based monitor that's calibrated to specific Navy hydrocarbons that looks at oil content. So you could get that information to try to see how much oil is there under different conditions.
Great, thank you so much, Gary, for entertaining the many questions that have come in today. At this point, we are going to go ahead and transition to our second speaker today, who is Ms. Danielle Painter. Danielle is a chemical engineer in the Naval Surface Warfare Center, Codrock Division's Environmental Engineering Science and Technology branch in Bethesda, Maryland. Danielle is the principal investigator on a variety of projects focused on the behavior and characterization of oil and water emulsions, electrochemistry, and ceramic membrane technology to treat Navy bilge water. She has co-authored over 10 technical reports, 4 peer-reviewed publications, and a patent. And as a result of her great work, she received the NSW CCD Command Award for Innovation a few years ago. Danielle earned a bachelor's degree in chemical engineering from Virginia Polytech Institute and State University, and a master's degree in environmental engineering from North Carolina State University. Danielle, please proceed.
First, I'm going to provide a brief overview of what bilgewater is and why bilgewater emulsions are so challenging, then discuss our research goals and objectives, as well as some experimental work that we've conducted, including characterization of shipboard cleaners, and how cleaner properties, environmental impacts, and fuel additives all affect emulsion stability. Finally, I'll wrap up with conclusions and next steps. The bilge is the lowest part of the hull, where the liquid drains from the interior spaces and upper decks of the vessel into holding tanks. Bilgewater composition is highly variable. It changes day to day and from ship to ship, and is primarily dependent upon shipboard tasks. In the photograph provided on the right, there are 4 extracted bilgewater samples. As you can see, the quality of the hydrocarbon phase as well as the turbidity or the clarity of the aqueous phase vary quite a bit across those 4 different samples. The presence of oil, water, and a soap or surfactant in these bilge systems enables the creation of oil and water emulsions, which are in particular very difficult to treat shipboard. The EPA, DoD, and OPNAV instructions all are consistent in saying that the oil discharge is limited to 15 parts per million. In order to meet these regulations, we have oil pollution abatement systems installed shipboard. They are comprised of 3 primary components, which are the oily waste holding tanks, so they're the holding tanks that contain all of our waste stream. And then we have our oil-water separator. The effluent of the oil-water separator then enters into our oil content monitor. The oil content monitor is the decision maker for determining whether or not the effluent can be discharged overboard or needs to be recirculated back into the holding tank for reprocessing. The oil-water separator is typically comprised of two different stages. The first stage is a gravity coalescence parallel plate separator, which uses the density differences of these large coalesced oil droplets to separate out these droplets from the bulk phase. Any small stable droplets are then processed by our membrane oil-water separator, which is comprised of ceramic membranes with a nominal pore size of 60 nanometers. The membrane oil-water separator is installed specifically to treat oil and water emulsions. The effluent from the membrane oil-water separator then enters into our oil content monitor. The Navy uses the ET35N oil content monitor, which leverages light diffraction or turbidity to determine whether or not the effluent is greater or less than 15 parts per million oil. If it's less than 15 parts per million oil, the effluent's discharged overboard, and if it's greater, it goes back into our oily waste holding tank for reprocessing. As you might imagine, a Navy ship has very limited space to hold wastewater. So it is very important for us to ensure that the treatment systems installed shipboard are capable of treating that waste stream, and so we can concentrate up the oil phase and then have enough capacity to hold that until we reach a port and can dispose of the contaminants. So the reason why bilgewater emulsions are so challenging is because surfactants or cleaners that are used in daily shipboard activities like engine, deck, surface cleanings, and washing surfaces all drain to the bilge. The variety of those surfactants and the composition are quite expansive because they are commercial surfactants and cleaners. And so that, along with any small particulates that come off during the washing process, can lead to emulsion formation. Emulsions, which are typically droplets less than 10 micrometers in size, can be suspended for extended weeks to years. So that means that our primary parallel plate separator is incapable of treating bilgewater emulsions. While we have a ceramic membrane secondary treatment system installed shipboard, we still want to make sure that the ceramic membranes remain intact and do not become fouled. And the more emulsions that we have in our system, the more likely that the ceramic membranes would need additional maintenance. As you can see on the figure on the right under anatomy of emulsion, typically we have this oil layer on top that can be removed by our primary parallel plate separator. Then we have beneath the oil layer a cream layer as well as an emulsion layer. Both the cream and emulsion layer would need to be processed by our ceramic membrane. By improving the understanding that we currently have regarding bilgewater emulsions, it'll allow us to determine if treatment systems are capable of meeting the requirements for oil removal as well as volume reduction. We also might be able to recommend different operational profiles based on specific maintenance tasks. For instance, based on a specific maintenance event that uses a specified cleaner, we might recommend that the operator wait an hour or two before processing, or potentially add seawater to the holding tanks to enable destabilization of the emulsions. In addition, if there are cleaners that are identified throughout this process as especially problematic, so in small quantities they can create very emulsified systems, then we might recommend that those cleaners be removed from use shipboard.
So our primary objective for research is to advance the current understanding of emulsions formed in armed forces vessels through emulsion characterization and modeling analysis. This is broken into three separate tasks. The first task is a scoping study, which included a literature, technical, and regulation review, shipboard personnel interviews, and then also identifying commonly procured Navy cleaners. The result of our task one was a review article that's published in the Science of the Total Environment, if anyone is interested in looking at that. The procurement
Identification of Navy cleaners was the foundation for our task 2 and the characterization of our prepared bilgewater emulsions. We also procured extracted bilgewater, so bilgewater from actual Navy ships, and characterized that as well. As a part of that, we looked at impact of cleaner properties, environmental impact, and fuel additives, all on emulsion stability. The data that was produced from task 2 is now being fed into our model to try and predict which parameters would be most helpful in identifying whether or not a cleaner would be problematic if found shipboard for emulsion stabilization. And we're currently working through task 3 this year. So as mentioned before, emulsions are formed when you have oil, water, and a soap or surfactant all present, and then either based on thermodynamics or agitation, an emulsion is formed. For our project, we're focusing primarily on the properties of the surfactants or cleaners. They're divided into 2 different categories: structural properties, which include hydrophilic lipophilic balance, so where exactly that surfactant sits at the interface, if it's more towards the aqueous or hydrophobic phase, and also surfactant interactions, surfactant lifetime, and chemical composition. In addition, we're also looking at physical properties, so the critical micelle concentration, or the concentration of surfactant at which the surface tension or interfacial tension is at equilibrium, as well as the interfacial tension, hydrophilic lipophilic deviation, and zeta potential. Really what we're trying to understand is there a property that can at least roughly describe how likely it is that a cleaner would be capable of emulsifying and causing issues shipboard to our treatment systems? And if we can determine that property experimentally, can that knowledge then be propagated out to other commercial surfactants so that it can improve our decision making, either in how we select surfactants for shipboard use or in how we operate systems shipboard? So as mentioned, our task 1, we have identified shipboard cleaners based on procurement information. The idea here is that we looked at the most commonly procured cleaners, the assumption being that if it was procured in the highest volume, it has the most likelihood of getting into the bilge. And you can see on the table on the right, the cleaner, and then the primary surfactants that are found in those commercial cleaners. We looked at properties including CMC, surface tension, interfacial tension using our Navy standard bilge mix number 4. Carrie had provided information on that in her slides, but we essentially, the NSBM number 4 is composed of marine diesel fuel and 2 different types of lube oils that are commonly found shipboard. We also looked at micelle size and zeta potential. One important thing to note is while the primary surfactants might be consistent across cleaners, this is not necessarily a good indication of how that cleaner might behave. And we found that and confirmed that by experimentally determining the properties listed here. So as mentioned, it's not necessarily straightforward by just looking at a surfactant alone, how these commercial cleaners would behave and emulsify oil. So they're composed of builders, which include things like that can alter water chemistry or improve surfactant efficiency. So they will buffer solutions and pH impacts will be reduced. They also have surfactants that can emulsify soil and oils and improve wetting. And bleach, which oxidizes organic surfactants, as well as other components including enzymes, foam regulators, corrosion inhibitors, optical brighteners, and fragrances. So knowing this information, we were curious if there were the experimentally determined properties could provide an indication universally about how these cleaners might behave shipboard. And so we looked both at some of the measurable properties as well as environmental impacts. And we used both reference surfactants, so surfactants without any of those additional components that you would find in commercial cleaners, as well as shipboard cleaners to determine if they were representative or comparable. The analysis we used were both emulsion stability, both looking at visual, so if there was an oil or cream layer, and then also measuring out a separated sample into aqueous cream and oil layers. In addition, we also looked at droplet size analysis. So the first parameter that we were interested in looking at is the role of CMC on emulsion stability. In literature, it's interesting because there are conflicting arguments between whether or not CMC is actually indicative of emulsification. It is indicative of formation, but not necessarily emulsification or improved emulsification of a system. So we looked at CMC-based reference surfactants first. We looked also at high-intensity homogenization, which was 20,000 RPM, as well as low-intensity homogenization, which just inverted samples, as well as varying the mineral oil content. So we had 20%, which is provided here, as well as 10%, which is provided on the next slide. And what we found is at 100% CMC, or at CMC, there is this inflection point. And from the sample being partially coalesced, so here's oil separation, and then you see it going down to 0 to fully emulsify above CMC. So this is an indication to us that CMC might be a good indicator of whether or not a system would become emulsified, or at least the concentration of surfactant that would be, or cleaners that might be required in order for the system to become emulsified. So looking at 10% mineral oil, we see that same inflection point between partially coalesced and fully emulsified systems. Now, this is only for reference surfactants, so we were curious if this data would also hold, or the trend would also hold for our commercial cleaners. These cleaners were selected based on having the widest range of experimental parameters just in terms of CMC and interfacial tension. So we wanted to make sure that we tested a wide variety of cleaners and how they behave to see if this particular metric would be appropriate for determining emulsification and how easily emulsified the system would be. So as you can see here, the point at which the system is partially coalesced versus fully emulsified is actually up to 10 times that in comparison to the actual CMC point, reference point. Now, knowing what we do, especially in conversations with our other collaborators on the project from Purdue and Lehigh, as well as Minnesota, so Dr. Dutcher, we decided to look at the interfacial tension rather than just surface tension of to determine CMC. So essentially, to determine CMC, you look at a range of different surfactant concentrations. The equilibrium point for surface tension or for interfacial tension is where the surfactant, that is the surfactant concentration, or the CMC, the critical micelle concentration. And so using the interfacial tension, which is the oil-water interface versus the air-water interface for surface tension, we saw that inflection point shifted back to 100%, so closer to the CMC for the 4 different surfactants or cleaners that we investigated. So this provides a good indication of, and potentially could be used for determining whether or not commercial cleaners would be cause any issues shipboard in terms of emulsification, because it's important to know not only the likelihood of it getting into the bilge, but also the quantities that might be required for the system to become fully emulsified. So some of these cleaners, it would only take a couple of gallons, while others, it could take hundreds of gallons. So next, we also looked at environmental impacts on emulsion stability. This is just a sample data point. We have our one cleaner blast off here at a single temperature. So we looked at different temperatures, pHs, and then also the addition of suspended solids or salts and the combination of those two. With this study, we just used visual observations of the coalesced layer, so whether or not there was oil, creaming in oil, or no coalescence. So you can see how we determined this by the figure on the right. So extending that data out, the rest of you can see in the diagram here, we have each type of cleaner and also their relative stability determined by oil or creaming in oil. Essentially, if you see less white, then it is less stable. And so this is provided in order of stability. You can see here what we determined was that, as expected, builders and other components in commercial cleaners have a significant impact on emulsion stability, and we cannot rely just on the primary surfactant as a reference point for whether a solution will actually be emulsified or not. Consistent with literature, we saw that salts and solids, as well as increasing temperatures, destabilize our emulsions, but pH had little impact. We think this is likely due to the buffers and other components that exist in bilge or in the commercial surfactants. Next, we wanted to look at the impact of fuel additives on emulsion stability. In previous experiments, we saw that there were additives in our hydrocarbon phase. We had previously never looked at, investigated the hydrocarbon phase as a potential source of emulsification. And so what we did is we wanted to determine exactly what those additives are and how they transport into the aqueous phase. And we did that by putting a layer of Bilgewater, or it's the NSBM number 4, on top of deionized water, and then let it rest for 24 hours and then extract it off the DI water to see how well that DI water, when mixed with a pure NSBM and its components, actually emulsified the system. So as you can see in the top graphic, we have just a visual representation of our work, and it's mineral oil with DI water after inverting and then letting rest for 1 hour. With the mineral oil with DI water alone, you can see that there is an obvious coalesced mineral oil layer, while the sample that was mixed with the NSBM number 4 extract water, it is completely emulsified. So in the bottom left, we have cream rate. This is the bar chart. We have cream rate per hour. For DI water, as you expect, there is a high cream rate, which indicates low stability. And then NSBM seems to be an average of the marine diesel fuel and the 2 lube oils that are contained in NSBM. This is consistent with our relative rate of creaming, which is the diagram that's provided on the right. And you can determine, based on the slope of the data points, the rate at which the sample destabilizes or creams. So in short, cleaners on ships vary in composition and chemical properties, and it makes Bilgewater emulsion stability prediction incredibly challenging. As Carrie mentioned, even the addition of 1 or 2 other surfactants to a system completely changes the behavior, can completely change the behavior of that system. So one of the most interesting findings of our work is that the CMC based on interfacial tension can be used to evaluate a cleaner's likelihood of emulsifying oil, at least for commercial cleaners, which we have not seen to date. We currently have a manuscript that's in preparation right now and planned for submission this week. So hopefully we'll have additional information on that coming soon. And also, as fairly consistent with literature, the Bilgewater emulsion stability is impacted by salinity and temperature, as well as fuel additives. For our future work, we'd like to actually identify what additives in the fuels are transporting into the aqueous phase and causing emulsion stabilization. We are also developing models using all of the data that we collected to determine parameters that are most likely to predict emulsion stability, and also help define turbidity and other methods of determining stability and how they relate to each other. Both of the models that we're using include classification, that's essentially a categorization method, as well as regression models, which is image analysis of our samples. And then we are also applying all the fundamental knowledge gained in this area to our aqueous film forming foam behavior. So there's a lot of interest in PFAS right now, and the way that foams are stabilized and emulsions are stabilized are actually quite similar. So for benefits to the DoD, we would like to look at more refined build management practices. So is it possible to provide information on how to alter the treatment system operational profiles based on specific shipboard activities or maintenance events? So as I mentioned, we may recommend, if you need to add salt water or something to the bilge, or if you should wait a specified amount of time before processing. We also believe that the gains here can improve treatment selection of appropriate bilgewater treatment technologies. So it's assessing the types of treatment systems that might be required in order to treat our bilge wastewater, and also assess new technologies that might become available and whether or not those technologies would be capable of separating out the kinds of waste streams that we see shipboard. There's also will be a more informed bilge cleaner selection. So we can actually test cleaners prior to them being approved, or if there are questions on whether or not something should be eliminated, we at least have a foundation for assessment. I'd like to acknowledge our excellent team, Dr. Jared Church, who works with me at the Naval Surface Warfare Center, Dr. Woo-Young Lee and Ms. Daniela Diaz, both from the University of Central Florida. They performed the environmental impact experiments and are also working on the modeling analysis. And then Dr. Jeffrey London for his expertise and facilities. Appreciate all of the hard work that everyone has put in to get the project to where it is today. And with that, I'm happy to take questions.
Thank you so much, Danielle. We're right on time, and we've got a number of questions that have come in. Let's start with this one. Are you able to meet with ship operators to help you identify what their requirements and desires are for bilgewater treatment?
Yes, we definitely are. And then, especially as a research scientist, it is a very different perspective. So the majority of the individuals who operate these systems are enlisted personnel who are in their late teens, early 20s. And so to select a system that is reliable, takes little maintenance and little burden for the operator, that's really what we're looking for. So if there's any way to reduce any of those burdens, that's what we're most interested in.
Great, thank you. And in your model work is really intriguing. Can you provide a little more detail regarding the model you are developing and its application?
Yes, so for our classification model, what we're doing is we're taking the environmental data and we essentially classify them into oil, oil cream, and no oil, and then determine based on the different parameters that we've tested, which parameters would be most likely to identify or are most important for determining emulsion stability. So this is really important because what we're trying to do is find a feasible method of determining emulsion stability without having to, excuse me, create thousands of emulsions especially if we have new cleaners. We don't want to have to go through a huge suite of testing. It would be nice if we could find that one sort of holy grail. And so one of the things that we're trying to do, especially because we did test so many different parameters, is try and understand how those different parameters affect one another, and which one is most important. The next thing that the other method that we're using is a regression method, which so we took photographs of all of our samples, and we're trying to combine the information not only for coalescent stability, so that's looking just at the hydrocarbon layer, so whether or not it's oil or oil and cream, but also combine that with the kinetic stability, so the turbidity of the bottom portion, so the aqueous portion of the sample. The reason why we're interested in looking at that is because we'll have to treat that entire sample. So there will be a portion that's capable of being treated by the parallel plate separator, but then the cream and the emulsion layer will likely need to go to a secondary treatment, which might be our ceramic membrane system. And depending on the concentration of the cream layer, that could be very problematic for us because it could foul the system and require additional maintenance and cleaning, which is something that we want to avoid. So it would help us identify potentially problematic cleaners, or at least how long it might take for those cream layers to coalesce further and be processable by our parallel plate separator.
Thank you so much, Danielle. You mentioned on your benefits to DoD slide that one of the benefits of the work that you're doing is improved selection of appropriate Bilgewater treatment technologies. You also referred to the issue of PFAS, and we will have upcoming webinars in October, to be specific, on PFAS treatment technologies, and also the work that is being done under this program area to try and develop fluorine-free foam. So given the interest in PFAS, can you speak and provide some initial thoughts on the types of treatment systems for shipboard activities that you refer to on slide 64, and whether those treatment systems are effective for PFAS?
So it's interesting. We have not tested any PFAS or aqueous foam forming foams specifically with our treatment systems, but one area that we are very interested in is how they might, so right now for at least Bilgewater oil and water emulsions, one of the best treatment systems that we have is the ceramic membrane technology. And knowing what we know about AFFF and how it works, we're curious about the interaction of those components with the membrane. So better understanding that, if it actually causes issues with the interfaces and the way that the surface of the membranes interact with the film forming foams, if those are actually compatible, or if we're going to have to figure out some other method, leveraging the mechanisms by which film forming foams function to separate them from solution. So it's an area that we're actively looking at. We have not tested any of these systems specifically for treatment for AFFF, but it is of interest and something that we've been actively talking about.
Thank you so much, Danielle. At this point, I'd like to pull Carrie back into the discussion, but we'll start with you, Danielle. Can you elaborate on how you're going to use or transition your research results to help inform DoD shipboard bilge issues? Danielle?
Yeah, so one area that we're actively working on right now, and that this project has definitely informed, is defining appropriate bilge cleaners. So we're looking for cleaners that will be short-lived, that so they won't remain emulsified for long periods of time. And now we finally have metrics for determining how to measure those bilge cleaners and their likelihood of emulsifying.
Thank you. Carrie, would you like to share your perspective?
Yeah, it's very similar. I think that by developing this database of different model parameters for the surfactants and then for the emulsion stability, and working closely with Danielle and Jerry Church and others at Carter Rock, that information can be used in that classification or regression model to help inform how the cleaners will perform and how much they will emulsify a bilge system.
Great, thank you both. I'm really curious to hear from you guys about any surprising findings that you've both encountered. Clearly, you've collaborated a lot, and that's great that you're leveraging several projects to help benefit DoD, but do you have any surprising results? And then what sort of key takeaway messages would you like to leave our audience with today? And Carrie, let's go ahead and start with you.
So in terms of surprising, I mentioned a couple about the phase mattering and about the role of the oil content. One thing we didn't talk about, but I know a number of groups are seeing, I know when I was Hori at Lehigh, and then the people at Purdue, and then all of us, is the role of spontaneous emulsification. That it's not just about agitating these emulsions and that they form oil droplets, but that if there's any sort of oil-water interface, you can actually have oil droplets that spontaneously form near that interface and produce a non-trivial amount of oil that goes into the cream in the emulsion phase. So that's just been very interesting to look at, and that's emerged as a part of this work. I don't know if we set out looking out for that. And then, sorry, really, what was the second question?
What sort of key takeaway messages would you like to leave our audience with today as we start to wrap up?
It's looking at things as a whole. So, we do try to isolate individual surfactants, but then how the surfactants behave together. Danielle did a great job talking about the role of the salts and the role of these solid particles, and how there's competitive or additive or synergistic interactions between these contaminants that really change the properties of these emulsions. And so just trying to look at it from that perspective as a whole to better understand these systems is important.
Thank you, Carrie. Danielle?
Yeah, so one of the things that has been most surprising is really just checking our assumptions regarding the hydrocarbon phase as a contributor to emulsion creation and finding that it does in fact have an impact. As I mentioned during the presentation, at least during my time at Carter Rock, we kind of took for granted the hydrocarbon phase and focused solely on these cleaners and surfactants as being the primary contributors to emulsification. And then after some digging and talking to fuel experts and determining that, nothing in science is ever as simple as it seems. There's always more depth to explore. And so it's just been really interesting and enjoyable going through this process of having an intuition, being able to explore it, and then coming out on the other side with experimental data that proves out that intuition. One other example of that was also determining that the IFT-based CMC seems to be a good indicator of emulsion formation and stability with respect to surfactant concentrations. And so I guess the key takeaway, as I kind of mentioned before, is that these systems are incredibly complicated, and it is important to look at them as a whole. But it's very rare that as researchers we get to be a part of a larger program where academia and the government laboratories are all working together. So being able to share that information and kind of bounce ideas off of one another about why something might be happening has really improved our knowledge about these systems and our ability to translate that knowledge into actionable solutions. Shipboard.
Thank you so much to both of you for a great webinar. I'd like to remind our audience members that our next webinar is on Thursday, June 20th in the Environmental Restoration Program area. This webinar will feature 2 speakers on innovative techniques to remediate 1,4-dioxane in the presence of chlorinated solvents. We'll have Dr. Bruce Rittman from Arizona State University, who will talk about the use of a hydrogen-based membrane palladium film reactor, followed by an oxygen-based membrane biofilm reactor in sequence to treat groundwater contaminated with 1,4-dioxane that is mixed with chlorinated solvents. Then we're going to have also Dr. Jens Blotzogel from Colorado State University, and he will summarize his work to couple electrochemical water treatment with biological degradation to remediate 1,4-dioxane in mixed plumes. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a moment to complete the short survey that will pop up on your screen. This concludes today's webcast. Thank you for your time.